Well, welcome to Math 120. This is Dennis Piankowski speaking, the instructor. We're going to get started on our video segments of the lessons with section 1.1. The video will be in several parts. The first part is just some introductory vocabulary. We're going to work through a pretty intense and very important problem in the second, and actually we'll do a third problem in the third segment. So let's get started here. Systems of linear equations. You're already familiar with elementary systems of linear equations. Here's an example. Solve 2x plus y equals 3, x minus 3y equals 5. You've seen problems like that in beginning algebra, probably years and years ago. And you know how to solve that. There is exactly one solution to this system. X equals 2, y equals negative 1, which we can write as an ordered pair, right? And we can interpret that system graphically. Each of the original equations has a graph that's a straight line, and the solution to the system is the point where the two lines cross. Now, sometimes a system of linear equations has no solution. Sometimes it has infinitely many solutions. No solution would be if the two lines were parallel to each other, right, and they didn't intersect at all. Infinitely many solutions is kind of boring in the two-dimensional case. It means the two lines coincide, they match up exactly. In our course, infinitely many solutions is going to be incredibly interesting because we're going to talk about what happens in 2, 3, 4, and higher dimensions. And the situation gets quite a bit more complicated than what you see in the two-dimensional XY plane situation. Let's just look at 3 dimensions for a moment. So here's a system of what are called linear equations in 3 variables, 3 equations, x plus y plus z equals 2, x minus z equals 4, 2x minus y plus z equals 5. So in this system, each equation has a graph that is a plane in 3-dimensional space. And you should be familiar with 3-dimensional space from Calculus 3. And you should be able to picture each one of these equations as a plane in space. And those 3 planes can intersect in one point, and this is a pretty lousy picture I drew. The solution is 1, 4, negative 3. So x equals 1, y equals 4, z equals negative 3. And we can visualize, this isn't exactly what this picture would look like for that system, but we can visualize 3 planes having just one point in common. Let's go on to the second page here. So, but 3 planes could also possibly intersect in other ways. 3 planes could intersect in a single line, or a plane. They could all coincide. Or they may have no common point of intersection. So with the situation with 3 variables in 3 dimensions, it starts getting a little bit more complicated than the 2-dimensional case. And we're going to look at even higher dimensions where the geometric picture gets even more complicated. And this is where linear algebra comes into play to describe these situations. Really, it's not necessary in low dimension, but it's really helpful when we get to higher dimensions. So in this course, instead of using x, y, or xyz, or wxyz for variables, we're going to use subscripts on x. So we're going to use x1, x2 for x and y, and x1, x2, x3 for xyz. And this notation allows us to use any number of variables. So the 2 examples we started with on the first page could be written as you see here. I'm not going to read them over. So here's the first example of 2 lines. Here's the second example of 3 planes. In general, a linear equation in the variables x1, x2 to xn is an equation that can be written in the form a1x1 plus a2xn plus on and on to an xn equals b, where a1, a2 through an in b are numbers. They're going to be real numbers for us. So here are just some examples of linear equation. Here's a linear equation in 4 variables. You can just read that on your own. It's okay for those coefficient numbers to be fractions, to be square roots, to be just about anything. Could be pi, e. But the variables are always to the first power. So for instance, 3x1 squared plus x2 equals 9 is not a linear equation because one variable is being squared. We also can never multiply variables together in a linear equation. So x1 minus 2x1 times x2 plus 3x2 equals 6 is not linear. When we multiply two variables together like that in algebra, we consider that a quadratic, x1 times x2, even though it isn't the same variable squared. So that's not linear. A system of linear equations is a collection of one or more linear equations. A solution to a system of linear equations in the variables x1, x2 through xn consists of a list of n numbers, s1, s2 to sn, that make each equation true when plugged in for the variables. And we're going to use the following vocabulary sometimes. A system is consistent if it has at least one solution, maybe more, maybe infinitely many. So we use the word consistent if we have one solution or even more than one solution. A system is inconsistent if it has no solution. So that word inconsistent is totally synonymous with saying there is no solution to the system. So that's our little introduction. We're going to start working on a problem in the part 2 video.